Knowing the equation for linear momentum is mass times velocity, it should make a lot of sense to you that the equation for angular momentum, capital L, is moment of inertia times your angular velocity, omega. Now that has units of Newton meter seconds or kilogram meters squared per second. Now if you were only dealing with point masses, then you could actually use this equation over here. Angular momentum is the radius cross the momentum, the tangential or linear momentum at that point, cross product. And whenever you break a cross product down, it's RP, standing for linear momentum, P sine theta, if we were just looking for the magnitude, not the direction. Of course, we know what linear momentum is, mass times velocity. So if you were dealing with just a point mass, you could use RMV sine theta. Now, that would actually apply in this problem down here that I'm about to do, but I'm still going to go back to the angular momentum equation, the base equation, pretending it's not a point mass, just so you can see where this idea comes from. I should also mention this R is the radius from the axis of rotation. So here it would be the radius from the sun, because that's the spot that my comet is going to rotate around. The reason you need sine theta is because if the velocity at this point is coming this way, the radius, note that you're going to end up having an angle there between them, and so that's where the sine theta. The only time that your sine theta is 90 degrees is whenever you're in a perfect circular orbit, or if you're in an ellipse at the very ends of the ellipse, at the minimal distance to the sun and the maximum distance. Now in this example problem, I have a comet orbiting the sun. This part over here is actually called the perihelon, the distance closest to the sun, and this spot over here is called the aphelion, the furthest distance away from the sun. You can see my distances, they're listed in gigameters, giga meaning times 10 to the 9th. Now in any closed system, angular momentum is conserved, meaning the initial angular momentum equals the final angular momentum. And of course we know the equation for angular momentum. It's moment of inertia times your angular velocity, and I'm going to label both of those initial and final, because both the moment of inertia and depending on what's going on, the angular momentum could change. Here I'm increasing the radius. I know the velocity, the tangential velocity might I point out, at the nearest point. Now since this is a point mass, I actually know the moments of inertia here, mr squared for each of these. Of course the radius is going to change. And I don't know about the tangential velocity, I know about the tangential velocity, and I'm looking for the tangential velocity over here at the aphelion, the furthest distance away, but my equation is in terms of angular velocity, so I'm going to change that around as well. So now actually substituting in for a point mass, my moment of inertia, mr squared. Now making sure to label my radius as initial, because notice the radiuses change. And then omega here is velocity divided by radius. That's the radius to the axis of rotation. And then the same thing happens here on the final side. And what you can see here is one of my radius cancels on each side. That leaves me with the mass that is unchanging here, because the comet's mass isn't changing. Actually, comets do lose mass in the form of gas as they come, especially as they come close to the sun, but we're neglecting that idea right now. So the mass, which is unchanging, the initial radius, I'm calling this my initial position over here, and then the initial velocity, and then my final mass doesn't change, final radius over here, and then final velocity. Notice this equation here is the same as this up here. The reason we don't have the sine theta on it is because sine theta is 90 degrees at the nearest and the furthest point from the sun. It wouldn't be at any other points around here. Since the mass is the same, I can cancel that out, leaving me, since mass was the same, divide both sides by it, leaving me only with the initial radius times the initial velocity equals the final radius times the final velocity. And then plugging in all my numbers, I made sure to convert back to base units from gigameters back to meters times 10 to the 9th, and from kilometers per second back to meters per second. That's actually going to end up being unneeded because things would end up canceling out and my answer would come out in kilometers per second. But just good habits, just in case. I end up coming out with 5 kilometers per second, because that's what happens with angular momentum. It's conserved, and so the further away you get, the further spread out the mass is, the slower it's going to turn. Kind of like with a figure skater, an ice skater. The further out the arms, the slower they turn. But whenever they pull their arms in, and so the moment of inertia goes down because the radius goes down, they start rotating much, much faster. Now, this idea of conservation of angular momentum holds true in all sorts of situations, ranging from neutron stars, or a star with a rather large radius, a little bit larger than our sun, collapsing down into an incredibly small radius, going from a normal star rotations per second all the way down to an incredible angular velocity, 30 revolutions per second, rotating so fast now that it actually, in some cases, is emitting electromagnetic energy through its magnetic poles, something we would call a pulsar. Gravity pulling all that mass in so much, a little bit's blown out in the form of a supernova, the vast majority, gravity pulling all of it in so quickly, so hard, increasing temperature so much that your electrons and protons fuse together into neutrons and rotating now because of conservation of angular momentum incredibly quickly. All the way to ice skaters and merry-go-rounds. Here, ice skaters, if you know its moment of inertia, or you know an equation for its moment of inertia, there, like a merry-go-round would be a solid disk, 1/2 mr squared, then you can end up solving, and as you can see, if you decrease the radius, you're going to get a higher angular velocity, and that also works whenever you're talking about mass. You can change the mass on an object also, thus changing its moment of inertia. If this ice skater, instead of bringing arms in, grabbed onto extra mass, that's going to end up changing your moment of inertia and thus change your angular velocity. Now you can also see in this problem and the previous problem, I actually didn't convert here. I left it in revolutions per second in both of them. In the case of the previous problem with the neutron star, I actually left my radiuses in kilometers because all of my units matched up consistently, so I knew all my units were going to cancel out. If you ever have any doubt, though, if units are going to cancel, always convert back to base units. Now, an interesting question in these sort of situations is, was the kinetic energy altered? Because we can obviously see that our angular velocity went up compared to what it was, 2 revolutions per second, now up to 6.4, and much of a much larger increase with the neutron star. So did we gain any kinetic energy? Well, the answer is actually yes. There will be a change in kinetic energy because the ice skater in gravity of the neutron star did work. The ice skater has to apply a force to her arms, pulling them in, and there's a displacement that occurs to the mass out here. The displacement of her arms comes in and the force comes in. So remember, work and energy, same thing. She does work on her arms, thus increases the kinetic energy here. So let's solve for how much kinetic energy increases, aka how much work she did. Remember, the equation for rotational kinetic energy is 1/2 moment of inertia angular velocity squared. Now, in this case, I actually do need to change my angular velocity in revolutions per second back to radians per second because no units are canceling out in this equation. My base unit over here is joules, and so I need everything else in base units as well. And after substituting in, I come out with around 4,000 joules of work. Whenever I'm setting this up, I probably didn't set my moments of inertia exactly right here. I was just trying to approximate in my head. But the ice skater in this situation did 4,000 joules of work pulling her arms in, thus causing the angular velocity to go up. And conservation of angular momentum, though, works one way or another. And like I said, this idea applies to anything that rotates. And so whenever you add mass or you change the velocity here, you can always calculate what new angular velocity it would turn out to have using conservation of angular momentum.